All right, let's get right into it. We're going to talk about a discovery that completely flipped our understanding of reality on its head. This is the story of the photoelectric effect, the tiny spark that basically kicked off all of quantum physics.
So picture this. You've got light, right? And it hits a piece of metal. And get this, it actually knocks tiny little particles, electrons, right off the surface. Seems simple enough, doesn't it? But 100 years ago, the way this happened, well, it drove physicists crazy. It broke every single rule they thought they understood about light.
So first things first, let's just look at the effect itself. What were scientists actually seeing? This is section 1, light's bizarre effect.
Okay, so what is this thing really? The photoelectric effect, it's just this. You shine light, any kind of electromagnetic radiation really, onto a metal surface and poof, electrons pop right off. But, and this is the first big clue in our mystery, it only happens if the light's frequency is high enough. You gotta remember that part, it's super important.
At first glance, this seemed totally straightforward. You know, shine a light, get an electron. Easy peasy. But then scientists started digging into the details. They started measuring things, like how fast are these electrons moving? How many of them are coming off? And what kind of light does it take? And that's when things got, well, just plain weird. The results made absolutely no sense.
And this is where we get to the real heart of the problem. Section 2, a puzzle that broke physics. Seriously, the data they collected was like a list of clues from a crime scene where none of the evidence pointed in the same direction. It was a total mind-bender.
Okay, so check out these clues. First off, the electrons flew out the instant the light hit. I mean, zero delay. Bam, instant. Second, if you made the light brighter, you got more electrons. Okay, that kind of makes sense, right? More light, more electrons. But here's the kicker, the part that broke everyone's brain. Making the light brighter did not make the electrons fly out any faster, not one bit. And the weirdest clue of all, if the light's frequency, think of it as its color, was below a certain point, nothing happened. You could blast that metal with the brightest, most intense low-frequency light in the world, and not a single electron would budge. The only way to get faster electrons was to change the color to a higher frequency.
So you can see why they were scratching their heads, right? I mean, according to everything they knew, all of classical physics, light was supposed to be a wave. And a brighter light meant a bigger, more energetic wave. It's like a bigger ocean wave hitting you with more force. So, shouldn't a bigger light wave kick those electrons out with more speed? It just should, but it didn't. Why?
The gap between theory and reality was just massive. The rulebook, the wave theory, said more intensity, faster electrons. But what they actually saw was more intensity, more electrons, but all at the same old speed. The rulebook also said, hey, any color of light should work, you might just have to wait a bit for the energy to soak in. But in the real world, nope. If the frequency was too low, you could wait until the end of time. Nothing, ever, happened.
There was just no escaping it. The established idea, this beautiful theory of light as a wave, it just couldn't explain what was happening. It was just wrong. Not for everything, but for this, it completely fell apart. Physics had hit a brick wall.
But just when it seemed like they were completely stuck, a radical new idea came along from a pretty unexpected place and turned everything upside down. Which brings us to section 3, Einstein's revolutionary idea.
Now, this idea didn't just pop out of nowhere. A few years earlier, in 1900, a guy named Max Planck had this interesting thought. To solve a totally different puzzle, he proposed that maybe energy wasn't smooth and continuous, but came in little distinct chunks, or quanta. It was a cool idea. But then, in 1905, a young patent clerk named Albert Einstein took that little seed of an idea and, well, he ran with it in a way no one saw coming. What Einstein proposed was it was so simple, but so incredibly bold. He said, what if light isn't just given off in these little packets? What if light is these packets? What if it travels through space not as a wave, but as a stream of individual particle-like things? Forget the wave. Imagine light as a hail of tiny, tiny energy bullets. And this little bullet of light got a name, the photon. And here is the absolute key to the whole thing. The energy of one of these photons has nothing to do with how bright the light is. Zero. A photon's energy depends only on its frequency or its color. So blue light is made of high-energy photons. Red light is made of lower-energy photons. Brightness is just how many photons you have.
So, you might be wondering, how does this one little idea, the photon, manage to solve every single piece of that baffling puzzle?
Well, let's find out. Section 4. How the photon solved it.
Okay, get ready for the aha moment, because this is where it all clicks into place. Let's go through our mystery clues one by one. Remember how the electrons were ejected instantly? Well, that's because it's a one-on-one collision. One photon hits one electron. It's like a tiny billiard ball hitting another. Instant. Okay, what about brighter light making more electrons? Simple. Brighter light just means more photons are flying out. More bullets in the air means more hits. Makes perfect sense. And that threshold frequency that was so weird? That's just the minimum energy a single photon needs to have to even be in the game. If a photon bullet isn't powerful enough, it just bounces off. And finally, why does a higher frequency mean faster electrons? Because a higher frequency photon is a more powerful bullet. It hits the electron with more oomph, giving it a bigger kick and sending it flying faster. See? Every single weird observation is explained perfectly.
So, the photoelectric effect wasn't just some curious little oddity anymore. It was the smoking gun. It was the hard, experimental proof that light, this thing we had all agreed was a wave for centuries, could also act, without a doubt, like a particle. And the fallout from this one discovery, oh man, it was huge. It changed everything. Which brings us to our last section, the dawn of quantum.
You see, this was never just about light. This was about reality itself. This discovery didn't just solve one problem, it kicked open the door to a whole new way of looking at the universe. This was the birth of quantum mechanics, that bizarre, wonderful, and mind-bending world that rules everything at the tiniest scales.
And so that leaves us with one last, truly mind-bending idea to chew on. This whole thing proved light is a particle, right? But we have tons of other experiments that prove just as conclusively that light is a wave. So how can it be both? What does it even mean for something to be a particle and a wave at the exact same time? That question, well, that's the whole ballgame. That's the mystery at the very heart of the quantum world.